Hey, welcome friends, and in this video I am going to discuss about Lewis acids, right? So the two very commonly used Lewis acids are boronic Lewis acids like BX3, X may be any halogen like fluorine, chlorine, etc. So BF3, BCl3, etc. and aluminium chloride, AlCl3, right? These Lewis acids are generally used. Now both of them are from group 13, right? Boron and aluminium both are from group 13, and their outermost orbital contains the 2s orbital has 2 electrons, and the 2p orbitals has only 1 electron. So these two orbitals are vacant, that is their outermost orbital, that is 2s and 2p, contains 3 electrons. Now, why they are Lewis acidic? So, whenever you have a compound which is coordinatively unsaturated, right? What is meant by coordinatively unsaturated? So, as you can see, uh, this molecule has 4 outer orbitals, right? And this using these 4 outer orbitals, it can achieve up to 4 coordination numbers. So boron and aluminium both can achieve up to 4 coordination number. So their highest possible coordination number is 4, but you can see in this BX3 or ALX3 they are tri-coordinated. That is they are one of the coordination position is vacant, right? And that's why they can accept electron at this particular position. So first of all, if we want to elucidate the structures of these two Lewis acids, we have to use our VSEPR theory, and I will use the shortcut which I discussed in my other video. So the shortcut is you have to count the electrons in the central atom. So each of the central atom contributes 3 electrons from the valence shell, and these substituents are monovalent, so they will each contribute 1 electron, and that's why 3 will contribute 3. So 3 plus 3 equal to 6, and when you divide it by 2 you will get 3. So this is called, this is, I represent this number by H, and if H is 3, that means it is sp2 hybridized, right? Now, so sp2 hybridized means these 3 bonds will be in plane. So these are 3 sp3 hybrid orbitals, and each will contain 1x. You can have aluminium here, and there will be a vacant p orbital, right? Now what happens is that these 3 orbitals contain 1 electron each, 2 electrons each, 2 bonding electrons, and now this p orbital, I can say it a pz orbital, right? This is a pz orbital, and this is in plane. These are x. So this is your xy plane, and this is z axis. So this is your pz orbital. Now you can see this pz orbital is vacant, and it can accept electron from a base. So let's say you have a methoxide anion, right? So methoxide anion is a base, and it can attack here, so it can donate its electron density to give you this complex, right? So this is how boronic acids or boronic halides act as Lewis acids. Same thing can occur with aluminium trihalides, right? Now if you compare the acidity of the Lewis acidity of the halides of this group 13 elements, so group 13 has which elements? So first boron, then aluminium, then gallium, then indium, then thallium. And if you take their trichloro compounds, let's say if you take their trichloro compounds, so what will be the order of Lewis acidity? Now uh, before discussing that, I have to mention one further point, that this is your boron. So this is your boron trihalide, right? And in halogen, there are two lone pairs which are available, right? Two lone pairs are available here, and because it has total of 7 electrons, any halogen, its outer shell contains total of say, 7 electrons, right? So one of the electron is used in bonding, and now it has three pairs of electrons which are free for donation. So these are two pairs, and another one pair will be also there, right? So these three pairs of elect so this is, sorry, actually it will be in this lobe here, right? So this is the halogens sp2 hybrid orbital, sp3, actually it is sp3, but when it will participate in bonding, it will be actually sp hybrid of the boron. So sorry, the halogen will use its sp hybrid. So sp hybrid we can represent it like this, and there are unhybridized p orbitals. So this sp hybrid is used in bonding, of which one lobe is used in bonding and another lobe contains the lone pair. Other lone pairs are placed in this pz orbital, and let's say it is your py axis. So this paz and py orbitals have other two pair of electrons. Now the boron will also have an unhybridized pz orbital, right? And you can see these two are parallel to each other, so they can overlap. So there we can represent it by resonance also. So let's say this is your boron halide, and because it is coordinatively unsaturated, so its unsaturation is compensated by this electron donation. Okay, we can represent this as a canonical structure like this. So this is plus, this is minus, right? So same type of structures can also be possible from here also, and from this also. So three equivalent resonance canonical structure will be there. Now you can see, if this thing occurs, then the p orbitals which was vacant and was used for its Lewis acidity, that is actually not available because it is already occupied by the electrons from these halogens. Now to compare the, so this is how this pi bonding, this extra pi bonding reduces the Lewis acid character of halogens, Lewis acid characters of your group 13 elements. Now if you compare the acidity of this acidity along this series, what you will see is that for BCl3, the p orbitals which I just discussed, the extra pi bonding, in this case it is between 2p and 3p. In case of aluminium it is 3p 3p. In case of gallium it is 4p 3p. So if you come across the group, you will see that the p orbital on the metal atom is increases in size and energy also. So that's why the matching between the chlorine 3p orbital and the central atom p orbital will be less along the series, and that's why the pi bonding character will decrease. What is the consequence of that? That means the decrease in pi contribution means your p orbital is totally available for accommodation of electron borne out by the base. So this p orbital can accept electron pair from base, and that's why the acidity will increase along the series. So it will increase. Now it is not that it is a continuous increase, because as you increase the size of the p orbital which is actually accepting your electron from the base, if the size increases, then also the matching between this orbital and your base homo, that is, let's say, methoxide, so it's homo, it will also be mismatched, and that's why uh, basicity will not acidity will not increase up to that. So it is found that it is initially increasing. So BCl3 it is less acidic than your AlCl3, but then gallium GaCl3, and up to that they are like same, right? So increase is not so much. Now this is one point. Another point is that let's say you have your let's say you have your boron, and combining this boron with different halogen like BF3, BCl3, BBr3, and Bi3. So what will be the order of acidity in this particular series of compounds? So in this case also you have to consider the effect of pi bonding. Now first of all, if you think only about the electronegativity, you may thought that due to the presence of fluorine here, it is more electron withdrawing, and that's why boron will have more positive charge in comparison to chlorine, because chlorine is less electronegative. So you will think that BF3 will be the strongest acid, but actually the reverse is true, right? So why is that? Because in case of BF3, the orbitals which are used in pi bonding, which decreases the acidity, is in this case also 2p, and in this case also 2p, because they both are from the same period, and that's why these orbital overlap is very strong. And strong orbital overlap means there will be the boron will be highly negatively polarized, and that's why it will not appreciate the approach of any base. That's why its acidity will be drastically reduced, right? And if you come across the series, what will happen? The size of the halogen X will decrease, and that's why the p orbital which is used in bonding is also increase in size, and this orbital matching will be less, and that's why the acidity will increase. So in this case the acidity will increase in this from top to bottom. So acidity will increase because of the mismatch of the two p orbitals. Now again, if you consider the solution phase, it is not actually the true sequence, because if you increase the size, let's say if you have Bi3, so it is initially planar, right? Now when a base approach here, it will be tetrahedral because it is now 4 coordinated. So there, when it becomes 4 coordinate tetrahedral, you can see this is large iodine groups are placed all close together, and that's why steric hindrance will be between them. So compared to this tri-coordinated structure, in this tetra-coordinated structure there will be more steric hindrance, and this effect of steric hindrance will be more for Bi3, then BBr3, then BCl3, because the size of iodine is largest, and that's why the increase of acidity will be not that much what we expect, right? So this is one thing. Now what about aluminium halides? So in case of aluminium halides like AlCl3, you can think about you can think same thing, that this chlorine 3p orbital and aluminium 3p orbitals. So chlorine has filled 3p orbital, and this is vacant 3, this is vacant. So they can overlap. You can think that they can overlap to give your same uh, resonance stabilization as we find in case of BCl3. But actually, aluminium chloride exists as dimer, right? So they exist as this type of dimer. So why is this? Because again, if you consider the size of orbital, it is a 3p orbital, and it is also a 3p orbital, and up to 2p orbitals, the pi bonding is very weak, because 3p orbitals means up to 2p orbitals. If you take 3p or 4p, this type of orbitals are diffused in character, and that's why their overlap is not good, right? And for pi bonding, inherently a weak bond than a sigma bond. So orbital overlap is very much important, and if your orbital is diffused, then your orbital matching will be very less, and that's why this type of stabilization is not effective in case of AlCl3. But again, aluminium is a larger atom than boron, and that's why it can compensate its coordinatively unsaturation by some other way, right? So what it will do, so two aluminium trihalides comes together. So let's say these are two aluminium, and now this lone pair it donates here, and this lone pair it donates here, right? So that's how they can generate this dimer. So this is this is actually X I represent by general halogen term. It can be chloride or bromide, right? X, X, X. Now you can see this is a sigma bond, right? This is a sigma bond. Now, if you consider sigma bond between sp3 hybridized orbital, so in this case it is sp3 hybridized, and this also use the 3p and 3s orbitals, but nevertheless this sigma bond involving this sp3 hybrid is stronger than pi bond. That's why this stabilization is more than your pi bond formation. So that's why this aluminium trichloride will fine for this dimerization. Now why boronic halides doesn't show this dimerization? So first of all, they are already stabilized by pi bonding interaction, and secondly, these type of dimers are not favorable for them because, say, see, for boron, they are smaller atoms, and you can write this in the board, right? You can write it in the board, but it is not favorable because these are very bulky, and this dimer will not be a favorable structure. But indeed there is a tendency of dimerization, because when you mix this BCl3 and BF3, you end up getting BCl2F plus BClF2. So how do you get this? It is believed that indeed these processes through the dimerization process, right? So they orient themselves like this. Okay. So this type of although the true dimerization doesn't happen, but a transition state like structure is there postulated like this. But due to the steric hindrance they again collapse by giving, so this will go so actually this will go here and this will go here, and you get your BClF2 and BCl2F, right? So this is the proposed mechanism how you get this. Now this is about your group 13 elements and their Lewis acidity and pi bonding interactions. Okay. One thing I should mention in this aspect is that, so let's say you have AlMe3, right? So you have trimethyl aluminium. So it will also exist as your dimer, right? So there will be two methyl groups, and your other two methyl groups will exist as dimer like this. Okay, so you can, if you expand this structure, you will see that in this case your methyl group is pentacoordinated, right? In this case the carbon atom is pentacoordinated, so this so it is, you can consider this carbon as a sp3 hybridized carbon. So this is sp3 lobe. Now this sp3 lobe is shared, right? It is shared between these two centers, so this structure is also possible. So these are about the Lewis acidity and structural features of group 13 elements, and I thought that I should also do some videos from inorganic chemistry and physical chemistry, not only from organic chemistry. That's why I did this video. And if you like this video, then let me know in comment section. And if you know other videos from inorganic or physical topic, you can tell me. So thank you for watching.